Okay, so today we're going to learn about torque. It's a word you've probably heard about, and we're just going to dive in and learn all about it. Okay, so torque, which we symbolize with the Greek letter tau, which is kind of like a fancy curvy T, is basically the rotational equivalent of force. So if you recall, you better recall that force is what causes an object to accelerate in a translational sense. Well, so too does torque cause an object to rotate to accelerate in an angular sense. So it causes an angular acceleration or alpha. So if the sum of the forces on an object equals zero, the object doesn't accelerate. If the sum of the forces, it can travel the same speed but doesn't accelerate. If the sum of the forces is non-zero, then the object must accelerate. Well, the same thing is true with torques. Okay, so if the sum of the torques is zero, the object doesn't undergo an angular acceleration. Its alpha is zero. It can have a constant omega, a constant angular velocity, but it's not going to change. But if there's a non-zero torque on the object, then it must undergo an angular acceleration. More on that later when we talk about Newton's second law of rotations. So, in order to calculate torques, and this is something you've got to get good at. Man, do they like to ask questions about this on the AP test. You've got to be able to figure out torque by looking at a diagram. So here you go. When you look at a diagram, so I have a wrench. Here is its axis of rotation. I'm applying a force here. And so if I want to calculate the torque, I use this equation here. So this is one you just got to put in your brain. You got to memorize this one. Torque is equal to the force applied times, in newtons, times the distance r away from the axis of rotation to where the force is applied. So how far away from the axis of rotation am I applying this force? And it's only the component of the force that's perpendicular to what we're going to call the line of action. So imagine a line coming out of here, and I just look at that force. If that force is perpendicular, then that's going to be sine of 90, which, by the way, this has to be in degrees, not radians. Okay. So, but if it's not at 90 degrees, then I'm going to have two angles. I'm going to have one that's less than 90 degrees and one that's more than 90 degrees. I take the sine of the one that's less than 90 degrees. Let's just try this here. I've got, in this first case here, let's just see how much torque is being applied. So torque is equal to the force 8 newtons applied 3 meters away from the axis of rotation at a 90-degree angle, which, so the sine of 90 is 1. I get 24 newton meters. And the torque's going to be measured in newton meters because, well, force is newtons and R is measured in meters. But what if I took that same 8 newtons of force and applied it at an angle? Okay, so now what I have is I have 8 newtons of force applied 3 meters away from the axis of rotation at an angle of 30 degrees. Then when I take the sine of that angle and multiply by that, I get 12 newton meters. Now, as with all rotational values that we're going to measure, we're going to want to assign the vectors, right? So I have to assign a direction to it. So I'm just going to use the right-hand rule when I do that. We've already talked about the right-hand rule. So it's worth noting that sometimes College Board will say, assume, so normally we will assume counterclockwise to be positive, but sometimes they'll say, assume positive to be clockwise. I've noticed they do that sometimes, so make sure you read the prompts. Okay, so let's just talk about when a torque will be positive or negative. Okay, so remember, unless we're told otherwise, we assume that a torque that's going to produce a clockwise torque is negative and a torque that's going to produce a counterclockwise force is positive. So in this case here, if I wanted to know what is the torque on here, I would say, well, 5 newtons times 4 meters at an angle of 50 degrees to the line of action. But I have to keep in mind this is going to cause this object to go in a clockwise sense, so it's going to be a negative torque that I'm applying here. So if a non-zero net torque acts on object, the object is going to have is going to have an angular acceleration in the direction of that net force. All right. So let's see what I've got here. Okay. So I've got two forces acting on this. I have a 4 Newton force acting 2 meters away at a 90-degree angle, and that's going to want to make it go in a clockwise or negative direction. So I would say I'm going to sum the forces acting on this to see what my net torque is. So I'm going to say -4 because that's going to make it rotate clockwise, times 2 times the sine of 90, plus, I'm just summing them. In this case, this is a positive force because this makes it want to go in the counterclockwise. So positive 6 times 2 times the sine of 30. And when I sum these up, I get -2. What that means is this object is going to undergo angular acceleration in a clockwise direction, in the negative direction. But if the net torque equals 0, then it's not going to rotate. And that leads us to an interesting series of problems called torque static problems. So if I look here, I have -4 newtons acting 2 meters away at 90, like I had before. Now I have 8 newtons acting at 32 meters away. And when I sum this up, I get 0. What that tells me is this object is not going to have any angular acceleration. So torque static problems are a fairly common type of problem that you'll see on the AP test. You'll see a couple, at least 2 or 3 of them on the test. So basically, this involves a system in which I have multiple torques acting on an object, but they're going to sum to 0. So there's no motion in the system. When I say static, it means it's not moving. Not only is it not accelerating, it's not moving. Usually, it could be moving, but usually it's not moving. And so it has no translational acceleration. It has no rotational acceleration. So that's sort of the structure of these types of problems. Let's take a look. It'll make more sense when we look at one here. Okay. So in torque statics, what I've basically got is this: the sum of the torques is 0, the sum of the forces equals 0, and I can combine these two things to solve some problems here. All right. So that there's no acceleration, either rotationally or translationally. Here's a classic type of setup. Like I say, you're going to get some variation of this exact problem on the test. So let's just see how this works. So I'm told, look, I've got I have a rigid object like a meter stick. I have 2 forces acting on it. It's just hanging here from the ceiling. And they're going to ask you to say, well, what are the 2 tensional forces? Well, how do you go about solving these problems? Well, there is a trick to it. So let's just learn the trick. Okay, so the trick is this. I have basically a system that's not moving. So I get to choose, well, you know what, let's go to the next slide. Okay. All right, so it doesn't matter what I choose as my axis of rotation because the object's not really rotating. All right, so since it's not actually rotating about any axis, I can choose whatever I want to call the axis. So what I want to do is I want to pick an axis of rotation that's going to make the problem easy to solve. And there is an answer to that, and it is this. So look what I've got here. I have a 5-meter long board. It has a mass of 20 kilograms. I have 2 ropes holding it up, one that's applying a tensional force at the 1-meter mark, and one that's applying a tensional force at the 3-meter mark. And I want to find out what the tension force is on both these cables. So here's the trick. The trick is, since the board isn't rotating, I get to choose what to call my axis of rotation. And I'm going to choose the axis of rotation to be where one of these forces is being applied. And here's why. Torque is equal to mr times sine theta, right? If that r is 0, then the torque is 0. So that way it simplifies the matter. So instead of having gravity and T1 and T2, I'm just going to say, let's call T1 right here. That's the axis of rotation. Since T1 is passing the axis of rotation, it causes no torque. Therefore, there are only 2 torques to worry about: gravitation acting on the center of mass, and T2 acting 2 meters away from the axis of rotation. But you got to be careful. I have to remember that 1 meter mark is the axis of rotation, not the 0 meter mark. Let's give it a try. So here's what I'm going to do. I'm going to say, here's my axis of rotation. So therefore, I know that gravitation is going to be 200 newtons, and it's going to act at the midpoint, at the center of mass of this board, which is the 2.5 meter marks. But the 2.5 meter mark, the center of mass of the board, is 1.5 meters away from the axis of rotation that I've chosen. So I'm going to say 20 newtons times 10 meters per second times 1.5 meters. That's the clockwise rotation. Since it's not actually rotating, it must be equal to the counterclockwise rotation, which is going to be T2 times an R of 2 meters. So T times 2 meters. And when I solve this, there's only one unknown, and that's T2. T2 is 150 newtons. It's so awesome. But we're not done yet, because I still got to figure out what is the tension on T1. Well, now instead of using torque, which I could do it with torque, but instead of using torque, I'm going to do it this way. I'm going to say, okay, well, I know this object is not accelerating. I'm talking about translational acceleration. It's not moving. So therefore, I can say, well, I know that the sum of T1 and T2 together have to add up to 200. Otherwise, this object would be accelerating in either the upward or downward direction. So I know that mg is 200. I know that T1 is 150. So therefore, T1 must be equal to 50 newtons. So clever, right? Okay. let's keep going here. Here is one they love to ask. They love to ask this one, okay? So what I've got is I have one end of a cable is attached. Here is applying tension force T. And the other is attached to the end of this board, this pole. Now, this pole is 12 kilograms of mass and 5 meters long. And the angle with which this makes to the board is 25 degrees. So what I want to find out is what is the magnitude of this tension force, and we're going to assume that there's just friction holding us in place. So I want to know what that friction force is. It's really similar to that other problem. I'll show you what I mean. Okay, so what I'm going to say is this: well, I get to choose whatever I want to be my axis of rotation. So I'm going to say this is my axis of rotation right here. Therefore, I've got two torques. I've got a clockwise torque and I've got a counterclockwise torque. Those are the only two acting on it. So I know that this is going to be 120 newtons, so 12 times 10, and it acts at the center mass of the system, which is 2.5 meters away from my axis of rotation. So 12 times 10 times 2.5, that's this torque. Now this torque here is going to be T, whatever that is, times 5 meters away, times, as we said, the sine of this angle here, so times the sine of 25. So when I solve it for T, I get 142 newtons. But I got to remember that in order to solve this next part, because now what I want to know is this. This force going in this direction is 142 newtons, but this plus the friction has to equal the mg of this board. Otherwise, this board would be accelerating upwards or downwards. So what I find is this. Then I say, okay, so I know I have mg down is equal to 120. And I know that this tensional force I found was 142 newtons, but the upward component of that is 142 times the sine of 25. So that plus the frictional force, which is acting this way since this wants to slide down, uh, have to add up to 120. And so when I solve this, I end up with, I have a 60 Newton frictional force. So it's very similar to that first problem we did, except we're using friction instead of tension as that second force. The ladder problem. Man, these are so classic. This is such a classic problem. Okay, so I've got a 6 meter long, 20 kilogram ladder on a carpeted floor leaning up against a frictionless wall. All right, and it makes a 60-degree angle with the floor. And so what I want to know is, what is the normal force exerted by the wall? What is the normal force exerted by the floor? And what is the frictional force exerted by the floor? It seems kind of tricky to deal with right now, but it's really not. So let's just try this here. So I'm going to just draw the forces. So mg is going to be 20 times 10, so 200 newtons acting at the center of mass, which is 3 meters up, pointing straight down. And since this is 60 degrees, this must be 30 degrees. Now I know that the normal force from the floor is pushing up this way, and the normal force from the wall must be pushing this way. And since the normal force is pushing this way and it's not accelerating, I know that the frictional force on the floor must be counteracting and pushing the other way. So the sum of these forces is adding up to 0. So I have 200 down and 200 up, an unknown to the left and an unknown to the right. And I wanna know those unknowns. So let's just try. So let's just see. Well, I already know what the normal force exerted by the floor is. It has to be 200 because there's no other upward force, and this 200 Newton ladder is not accelerating. Okay. So let's just figure out what this normal force is. So what I'm going to do is this. I'm really going to make life simple. I have two forces acting through this one point here. That's going to be my axis of rotation. So those both, the torque caused by both of those just goes to 0. So then I've just got this system here. So I've got two torques. I have a clockwise torque and I have a counterclockwise torque. So the clockwise torque is well, so we'll talk about the counterclockwise force. So the normal force on the wall times the 6 meter ladder times this angle here. Since this angle here is 60, this angle here is 60 times 60. Plus, this is going to be a negative force, right? So I have negative 200 times 3, since it's actually the center of mass. And this angle here is 30 times the sine of 30. That all has to equal 0. And when I solve it, I get a normal force of 57.7 newtons to the left, and therefore my frictional force must be the same pointing in the other direction. Otherwise, the object would be moving to the left or the right. Hey, thanks for watching. Sorry this one took so long.